Hello stats enthusiasts, Goldie here, and we are at the final video in our Unit 6 series. Unit 6 has all been about inference for categorical data proportions. And in this last video, we are on Notes 8, talking about a significance test for a difference in proportions. And we're going to learn all about what this is, what this test does for us, and how we can use it to solve our problems. So pull up a chair, let's get our notes ready to explore this content. To set up our significance test for a difference between two proportions, there's going to be a few things that are different from this significance test that we're about to run and what we have done before when dealing with only one proportion. A lot of the steps are going to be the same. We're just going to do a few things differently. One of the things we're going to do differently is the hypotheses that we set up. The way you will usually see your hypotheses set up when you're testing between a difference is going to be our null having P1 equal to P2 and our alternative being the relationship between those either less than, greater than, or not equal to. So in that blank, you would have less than, greater than, or not equal to, depending on the context of the problem. Okay, so our null is always going to be that statement of no difference. Remember that I kind of said that before when we were bringing up significance tests, how your null is always a statement of no difference. Well, that directly relates to looking at the difference between two proportions. Our null is always no difference. And if we assume there's no difference, that means that we assume that they are equal to each other. And that's why your null is always equal to. Another way you will see it that some textbooks use is actually putting the difference, that subtraction on one side and then 0 on the other side. And you could really set it up either way. On a free response problem, either of these are correct, okay? What this does is, like, algebraically, if you subtract P2 from this, you get P1 minus P2 and you're left with 0 on the right side, okay? And this is also a way to communicate it because this says that 0 is your null difference, okay? That there is no difference, right? Algebraically, if P1 minus P2 equals 0, that means that they were the same value, that they were 0, okay? And then this would be the same thing, greater than, less than, greater than, or not equal to 0, okay? So setting up your hypotheses is going to look like this. Your conditions are going to be the same that they were for confidence intervals, except for one small but important change, okay? Normal. Both distributions must satisfy the large counts conditions in order to be normal. Now, here's the difference, okay? Here's the difference between confidence intervals and significance testing for a difference in two proportions. We are going to use something called P sub C in our normal condition check. We take N1 times P sub C, and this is supposed to be N1 times 1 minus P sub C. Sorry, a little copy and paste error. N2 times P sub C and N2 times 1 minus P sub C. So we are going to do that for both sample sizes, but for both sample sizes, we use that value P sub C. Now, what is P sub C? We're going to talk about that on the next slide, okay? So give me a second. We are going to talk about what that P sub C is. Finishing off our conditions, the other two conditions are going to be the same as they've always been. Random, they have to be both randomly selected or both random assignment. And independent, if you're sampling, they both must satisfy the 10% condition. Random and independent have not changed. It's just the normal with that P sub C. What is that P sub C? That is our pooled sample proportion. So that's a new term, pooled. P sub C is the pooled sample proportion. Think of the C as combined. The C stands for combined. So it's the pooled sample proportion. And the way we calculate it is with this formula. We take our X values from each sample and add them together and divide it by both of our sample sizes added together. That's how it's found, but what is it exactly? Well, we use this pooled sample proportion to calculate both the standard deviation and to check for normality because we always assume that the null hypothesis has no difference between our two proportions. And if we have an assumption that there's no difference between our two proportions, we assume that both successes come from the same pool, is how I say it. They come from the same pool. If there's no difference, they come from that same pool. So that's why we combine them together underneath a significance test. It's because of that assumption of no difference. Okay? We use this only for a significance test because this is a assumption we make only under significance test. So you are only going to see this pooled proportion underneath a significance test. We use this to check that large counts condition and to find the sample standard deviation or the standard error. We use P sub C to check the large counts condition and to find that standard error. Okay? So that's new. And that's only going to be true for a difference between two proportion significance test. When we calculate the p-value, we name the test. This is a two proportion Z test. And we calculate this test statistic like we have been. We have our statistic minus our parameter divided by our standard error. So our statistic is going to be what the difference is between our two sample proportions. And then our parameter is always, it's assumed no difference, right? So that's why it's minus 0. And then in the denominator, we have our pooled sample proportion that we use in our standard deviation. Again, because we assume the null is true, we base the standard deviation off of that assumption that the null is true and that the proportions come from that same pool. What you might see is a simplification of this formula. Because minus 0 is just like blah in algebra, we get rid of that. And then because both of these terms have the same numerator, a lot of the times you'll see that numerator factored out. So this is how you'll typically see it written. We have just a numerator p hat sub 1 minus p hat sub 2, because again, minusing our parameter is just 0, so we just drop that. And then we factor out the numerator between these two values, okay? So you'll see it kind of written either way. But once we have that Z, we find our p-value using normal CDF like we always do, okay? On the AP Stat formula sheet, again, standardized test statistic is right here, okay? So we have that statistic, our parameter is 0, and then remember for our standardized test statistic, we're not looking at the standard error of statistic, we are looking at the pooled proportion, and that's where this piece down here comes in. So for two populations, remember we use this for our confidence interval, but when P1 equal P2 is assumed, which it is in a significance test, then we use this as our standard error for our P hat sub 1 minus P hat sub 2. So you can see they're using that as your standard error. Okay, and you'll see that P, sometimes it's called P hat sub C, P hat sub C, that's fine, whether or not you use the hat, but you can see how it's factored out there. And then P hat sub C being those two X values added together, divided by that added together sample sizes. Oof, I said that a little weird, but please forgive me. Let's look at an example. We'll do a complete 4-step 4C process of this example, our two proportion Z test. So is there a significant difference in the smoking habits of the younger and older generation? So in a random sample of 600 young adults, it was found 180 of them had smoked in the past week. A separate random sample of 500 older adults, 185 of them had smoked in the past week. Conduct a significance test at the 5% level to determine if there's evidence to suggest that the proportion of smokers differs. Okay, so a few key things here before we set it up. We want to conduct a significance test. Okay, to conduct a significance test if there's evidence to suggest that the proportion differs. Okay, so we don't suspect that one would be greater than the other, even though our sample statistics tell us that one proportion is greater than the other. We do not set up our hypotheses looking at our sample statistics. We look at what we originally wanted to investigate, which is just if it differs. Okay, So that's important, setting up our hypotheses. Let's first define what our parameters are. So P1 is the proportion of young adults who smoke, and P2 is the proportion of old adults who smoke. Remember I said you could also use like P sub Y and P sub O if you wanted to, or something like that. You can use letters, but I'll stick with 1 and 2. We want to write down our significance level that we are using, followed up by our hypotheses. Okay? So our null is the statement of no difference, that there's no difference between these two proportions. And our alternative is that we are trying to see if there is a difference, if there's a difference between young adults and old adults' smoking habits. So that's our null and alternative hypotheses. We can also write down a bit more information here about what's given in our problem. So we do have our P sub C. We do need to find that value, and we do want to show the work that goes along with that. So we'll have our two X values from our young adults and our old adults added together, divided by our sample sizes added together. And that's 0.332. And then you can also write down, this is supposed to be P hat sub 1 and P hat sub 2, but you can also write down your sample proportions if you would like to write those down as well. We do still need those for our numerator of our test statistic, so we want to have those, but we are not going to use them for large counts, and we are not going to use them for our standard deviation. Let's go ahead and check our conditions now. So this all took place as our communicate piece. We are communicating the information in the problem and what we're trying to find. So let's check the conditions. Both samples were randomly selected. Perfect. Independent, we sampled. So let's check our two 10% conditions. And both of these are fair assumptions to make in terms of the population size. So we're good on independence. And then normal. Normal, I have to use P sub C. And I check it versus my young adult sample size. And then I use P sub C, and I check it with my old adult sample size. And you can look at that, all four of them are greater than or equal to 10, so this checks out. Okay, again, we use P sub C or P hat sub C because we are doing the pooled proportion with the assumption that the null is true. And when we make our sampling distribution with the assumption that the null is true, we have to use our pooled proportion to check that normality. Okay. Now calculate. We're doing a 2 proportion Z test. I'm going to write down my formula. Okay. I actually kind of mixed these formulas. I don't know. I don't really like the factored out piece, which I know is shocking for a math teacher to not like something factored. But in my head, this is always how I pictured the formula. So you can use the factored out piece of the formula. That is totally fine. You can use it this way. Both ways are accepted. You really only have to do one of these. I keep saying it because I want to remind you. On the AP exam, just one or the other is fine. I put them both down because these are notes and we're learning, but just one of them. Either name the test by name or name it by the formula. You do have to show all of these values combined too. Sorry, that got out of my square root symbol. But yep, you have to show all of these values combined. You do have to show those values put into the formula. So this second piece of the formula here is not an option. You do want to show all of these plugged into that formula. So in your numerator, you use your P hat sub 1, P hat sub 2, and in the denominator, you use your pooled sample proportion here. And then you can find your Z value, okay? And that's negative 2.455. All right. And then from there, we find the P value. Okay, so here's what we do on the calculator to remind you. We use normal CDF because my Z is negative, okay, just to remind you on a two-sided test, okay, assuming when we have 0 in the middle, this is our Z value, and we always want to find our P value as extreme or more extreme in the direction of the alternative. So for a two-sided test, okay, this is our P value, this is our Z value, and our P value, we want to find this area right here, okay? And that's what I did in this first step. Normal CDF, lower boundary negative infinity, upper boundary is negative 2.455, 0 as my mean, and 1 as my standard deviation. But it's two-sided, okay? So that means we also have to take into account the p-value over on this side. Okay? And you could use normal CDF again to find this, or because of symmetry, you can just take this value that you find and multiply it by 2, which is what I did in my calculator here. And we get 0.014 as our p-value. And then conclude, okay? Conclude, write 2 sentences. Because our p-value of 0.014 is less than alpha equals 0.05, we reject our null hypothesis. So that is our statistical conclusion. Okay? And then we need our context. Please never forget your context. We always want to put context to this stuff. We have convincing evidence that the proportion of young adults and old adults who smoke is different from each other. Okay? So we have convincing evidence of our alternative in context there. And that's our 4-step process. Okay? I have 2 follow-up questions here about this, just kind of pulling in some of the information we've talked about from our other sets of notes. A, what type of error could we have made in the example above? Now, if you ever are asked what type of error, or if you are asked to interpret errors, remember I say write down this table, okay? Help orientate yourself on where type 1, type 2, and power is in truth and decision. So work on memorizing this table. You will need it. What type of error could we have made? Well, what we decided to reject our null, which means we went in favor of the alternative. Now, if we went in favor of the alternative, which error could we have made? Type 1, okay? That's why the table is nice. It draws your eyes. You can visualize what error you might have made. So what type of error could we have made? Because we rejected our null hypothesis, we could have done that incorrectly, and that would be a type 1 error if we were to do that. Okay. It didn't ask us to interpret the error or draw anything, any conclusions about it. It just wanted us to explain what error we could have made. And then B, find a 95% confidence interval using your calculator. So don't do a 4-step process for this. Interpret it and explain how it confirms your results from above. Okay. Now, our results, we had a null equal to our alternative was P1 not equal to P2. Okay. So because we had an alternative that was not equal to, we can draw in a confidence interval. The other thing we had to check, we used a 5% significance level. And because we used a 5% significance level, that corresponds directly to a 95% confidence interval. So because those 2 things are true, we can use a confidence interval to help us interpret our significance test results. Okay? So here is how we would put that data in our calculator. Okay? So to prop z int to create our confidence interval, x sub 1, n sub 1, x sub 2, n sub 2. Calculate. Okay? And this is what it gives. Okay. Now, how does this confirm our results? This is our interval. Okay. You notice how it is negative. It is a negative interval. Okay. So because our interval does not contain our null hypothesis, remember our null hypothesis was they were equal to, and if they are equal to each other, that means that when you subtract them, when you find that difference, it is going to be 0. So because this interval does not contain 0, we would reject the null hypothesis in a 2-sided significance test of alpha equals 0.05. The last thing I want to talk about in this section of notes is going to be how to use the calculator, the TI-84, to do a 2-proportion Z test. So it's going to be under test, as they always seem to be. This is a 2-prop Z test, number 6. It's going to ask for your X1, N1, X2, N2. It's going to ask for your alternative, and it's going to return our Z value. When it says P equals, that's going to be our P value. p hat sub 1, p hat sub 2, and then it's going to return just a p hat. And that represents the pooled sample proportion. Okay, so there's a lot of p's that this calculator test returns. So I just want to make sure that you are keeping them straight. P equals is your p value. These are your sample proportions each individually. And then p hat is that pooled proportion, right, that you find doing x1 plus x2 over n1 plus n2. Okay? I just don't want you to get that confused when you see that on your calculator. And that wraps up today's video, as well as the unit on inference for categorical data proportions. Unit 6 is now finished. We have finished this last video here. We are now going to be moving on to Unit 7. So the Unit 7 playlist is what you're going to be looking for next. And in Unit 7, we're going to talk about inference for quantitative data. And we're going to be focusing on means. A lot of the same information we have learned about in Unit 6, such as confidence intervals and significance test, it will carry over into means. But there's also going to be some new things like our t-distribution that we get to explore as well. So take a look for that playlist, and that's where you're going to be going to next. If you liked this video, be sure to click the like button and subscribe to my YouTube channel for all the great AP statistics updates. As always, I wish you endless statistical success. Thank you guys for following along, and I will see you next time.